Today we're starting a game development series where we're gonna build a snake game clone. But we're gonna take it way beyond the basics. What we're gonna produce is a glowing, clone-dodging, retro-fuel challenge. Let me show you the end result that we're gonna strive to achieve. Here is our usual snake game, and once we eat our food, a snake clone is then spawned that will replay your path. And the longer you play the game, the deadlier these clones become. We will apply post-processing effects using shaders. You will see how glow or bloom filter is done. We will have chromatic aberration and scanlines for that retro feel. We will have pixelated view, some responsive gameplay, and dynamic UI feedback. Hopefully we will be able to find some free sounds for our game as well. Every single episode is going to focus on one or two things only, so that we keep it short and to the point. Today's episode is all about setting up Raylib's main loop and start working on the pixel-perfect grid rendering system that will power pretty much everything else in our game. Raylib is a simple library for video games programming. It has a really nice website with tons of examples, cheat sheet and wiki. It can explain everything that you want to achieve. This is something that we're going to use today. So to get started, we need to create our repo. We will name our project Snake Rewind. Once again, we will use CProgramming language with Raylib library. Raylib has a lot of bindings for different languages, so you can follow along using different language if you want. So let's jump into our project, and first of all, I have a template for CMake. Let me show you what it does. Pretty much tells us that, hey, we're going to be using C with C23 standard. We're going to export some JSON file from my LSP, have some compile options. We will compile everything in src folder, and we require Raylib, which should be installed on your system. Let's now create our folder, src, touch our main C, and create our main function, just to verify that everything is working. Let's see. And we now have Snake Rewind, and it works. Again, let's, as usually, create an alias so that we don't need to type these things out all the time. Let's check how our alias works. It works just fine. Great. So we can start on our Raylib main loop. And to do that, we can jump to the Raylib's site and just have a look at one of the examples there. This one I like because it's very short, simple, to the point, provides the main loop which we need, so we can test things out using it. We need to include raylib.h. Yeah, let's clean it up a bit later on, check that everything works. Yeah, seems to be working just fine. So let's clean things up a bit, see what we need, see what we don't need. All right, so with Raylib, it is as easy as that. I'm gonna extract these things and simply define some base width. base height. We can now search and replace screen width with base width, and we can search for screen height, replace it with base height, and here is our window. I'm probably not going to use this sizing, although I want to keep that aspect ratio. So I will define a window width, and I will define window height, which is going to be base width times some scale and base height times some scale. Now we need to substitute here for base width, substitute this window, let's do substitution first. Base height with window height, and provide that scale, which will be like something 75%. And if we run it, our window keeps the same aspect ratio, but it's a bit smaller. One thing that I would like to introduce right away is a sort of pixelated view. One of the examples here shows you how to do that. Pretty much you end up having a window of particular size, but then you render everything onto a texture, or you can think of it as an image behind the scenes, which has the same aspect ratio, but the size is much smaller. And then you let like OpenGL render everything onto the window and upscale everything, and you get this nice pixelated view for free. To achieve that effect, we need to create the texture target, right, which is going to use game width and game height. And we need to define it here again. Which is going to be something like base width by 2. And same for base height. Something like that. Then we need to do all our rendering onto that texture. Right? So we need to say, hey, draw me everything in this texture mode. If we do that, we won't see anything. That's because we have rendered everything onto the texture, but when we render things onto the screen, into our window, we do not render that texture. To do that, we need to say, hey, draw me some texture. Let's use this Pro thingy. So it's going to be target texture. Right, let's break it down line by line. Source rectangle is as easy as let's take the whole rectangle game width, game height. So we're saying take everything from our texture. Destination rectangle says, hey, render it onto the whole window. Origin, we keep it by default 0. There will be no rotation and no tint, so we keep it as white. And now we should see everything as before. Oops, we can see that the image is now flipped. And the thing here is is that Raylib uses y-axis 0, 0 or 0 y-axis in its top left corner, while OpenGL I think uses bottom left corner. So when we do this rendering, we need to flip the y-axis, and then everything should work as before. Right now we are rendering our picture onto the texture, and then this texture gets upscaled. So this concludes the main loop with Pixelated view, and we can start working on our grid. We can probably drop everything that we drew and start thinking about what the grid is like. Let's first of all define some structures. So game will have something like a tile grid containing rows and columns of some tiles struct. Let's define tile. For now the tile is simply TileState, and TileState is an enum. For now we will use like empty tile and visited tile. Once we develop our game, we will have a bit more enum values here. Our tile will have a bit more entries in it, and the game will also have a bit more entries in it. Next we define rows and some columns. Right, then we can define some tile size and some tile spacing, so space between the tiles. So how many rows will we have? Probably something like 14, columns something like 26, size, tile spacing something like that. Now our game width, just for the future reference, it's 960. We will have a global game variable, as our game is quite small. I believe this is fine to have just a global and reference it from other function places. So first we need to init our game. Before we enter our while loop, we can say, okay, init game, and I'm just going to use the Raylib's convention of this snake case. For now we have only tile grid to init, so let's do that. Init tile grid, which is another function, init tile grid. And in order to init it, we need to iterate over every single row, every single column, and yeah, we can say that, hey, we have a tile which is game tile grid at row column, and we can say tile state is empty tile, right? So the first thing we do is we initialize the grid, saying that every single tile is empty. Next, every single frame, we can now draw that tile. So let's first of all clear everything as black. Texture is also going to be black. And then we can say, hey, please draw me a tile grid. This is invoked in while loop, every single frame. How do we draw a tile? Tile grid. All right, I think we can grab this for loop, drop this one, and we can say, hey, every single tile in our grid is a square. So let's draw that. So we can use draw rectangle, something like this. We will have position, size, and color. Let's start with color. Our color is going to be based on the tile state. So let's define our function, get tile color, based on tile state. We switch on that state. In case it's an empty tile, we can return some color. It's a struct, so something like near black, like very dark gray, with alpha set to 255. Case visited tile, we can return something like 50-50-50, also gray, but a bit lighter. Next is size, vector 2. Size is vector 2. X is something and Y is something. Really, because our tile is a square, we can say that, hey, this is as simple as tile size and tile size. All that is left is to define position. Position is also a vector. We can say that, hey, this is our position. So we need to define draw X as something and draw Y as something. So really, in our grid, we need to take where are we at which row, at which column, and then make adjustments based on our tile size and spacing. So for X, we do column times tile size plus tile spacing, and for Y, we do row times same stuff. Let's try running it. See what happens. Alright, so this is our grid that we have. Currently it's being drawn starting from 0, 0, top left corner. We would like to align it horizontally so that the spacing on the left and spacing on the right is the same, and then just move it down a bit towards the bottom side of the window. To do that, we need to say that, hey, there will be some offset for X and there will be some offset for Y. Let's try to define those. Define grid offset X as something and define grid offset Y as something. Let's first define 0 and something like 35, I don't know. Yeah, so we've moved the grid to the bottom, which is fine. There will be some text at the top. Should be enough space for that. Now we need to calculate how much spacing we need on the left and on the right. So that's where our game width comes into play. So we have calculated that this is 960. We have these many columns, 26. So 26 columns. We need to multiply it by 32 plus 4. So each tile has like a square of size 32 by 32. And then there is spacing, 2 to the left, 2 to the right. This is 936 if I'm not mistaken. So then what is left is 24 pixels. That means we have 12 pixels on the left, 12 pixels on the right. That is what our offset X is going to be. If we run it, it kind of looks nice, but you can even visually see that the left side is a bit narrower than the right side, even though all the calculation seems to be correct. And the thing is that this draw X and draw Y is actually like a top left corner of the rectangle into which we're drawing the tile. But the tile, as I said, is a square which has spacing to the left, to the right, on top and bottom. Which means that inside of it, in order to draw it, we need to draw it inside of it, and we need to say that, hey, I need to offset a bit by tile spacing divided by 2. We divided by 2 because there is a spacing on the left and on the right. And say for Y, tile spacing by 2. If we run it, we can see that, hey, now the spacing on the left and on the right seems to be just about correct. Next thing, let me show you draw something like lines, probably. Let's break it down line by line. So I want to show you the container border. It will have line thickness of 1, it will have some gray color, and it will have some rectangle. We have X, we have Y, we have width, and we have height. So width is tile size plus tile spacing. Same here. X is draw X and Y is draw Y. Let's see. Yeah, pretty much it shows you that, hey, this is the border, and I'm showing it you because we have different states for our tile, and we want to change the size of this tile or the square that we show to half size when the tile state is empty, which means that the size that we want to draw, we want to tell it that, hey, if tile state is empty, then please use the halved tile size, otherwise full tile size. If tile state is empty, then same logic applies for Y as well. And now this grid shows you, let me change some color a bit first so that it's more visible, is that the smaller tile square is not in the center of this container. And it is not in the center because our position doesn't take into account the size of the tile. So right now it kind of thinks that it will use full tile size. So we need to adjust that again by saying that if it's an empty tile, right, then we need to take tile size and divide it by 4. Why do we divide it by 4? It's because we want to show only half the tile size, right? So another half of tile size is not shown, which means that when we draw this half tile size, there is a space to the left of tile size divided by 4 and to the right. Now if we run it, we can see that they are now correctly placed in the middle. We can drop our lines. Now it looks like this. And for the sake of example, let's show you what if our state in the tile grid is different. So for example, if row is bigger than 5 and row is less than 10, if column is bigger than 3 and column less than 7, let's say that tile state is visited. It now shows you how it's rendered differently, right? So these are not visited, empty, there is nothing, but once our snake visits a tile, we set the flag that, okay, it's visited, and it will be displayed like this. This is what our grid looks like. One more thing I would like to add is to animate the empty tiles. So these small squares, let's have some animation. Let's add some animation to them. To do that, we need to keep track of 2 things, like an angle of a tile and some timer. So each tile has its own timer so that they don't spin all exactly at the same angle, same timer. Yeah, you will see the effect once we implement it. First, we need to, of course, initialize these new properties that we added. You need tile grid. It's done right here. Yeah, so let's say tile angle is 0 for everyone. Everyone starts with the same, doesn't really matter. But the timer, we want to say that, hey, we want the timers to be different so that everyone starts at its own angle. And we could simply add some random, generated random in some interval, but we already have some row and column here, so let's use that. Let's say so here we're pretty much saying that timer is some value which represents our x coordinate times y coordinate, right? And we do the +1 because otherwise, because our row and column start from 0, otherwise like lots of timers will have zeros. We don't want that. So right now it doesn't really change anything. Our grid remains the same, and that's because we don't do any rotation yet. To do the rotation, we need to, of course, first update tile grid, and we need to have some sort of delta time, how much time has passed since previous frame, and this is easily accessible in Raylib using get frame time. And now we need to introduce this new function, update tile grid tt. What it does, again, we need to iterate, and for each tile we need to say that, hey, tile timer, we can add this tt to it, and then say that, hey, angle is actually sinus of this tile timer. This comes from math, and if we run it, we don't really see anything. That is because we do not, this is simply data, and it is not used in rendering yet. So when we draw a tile grid, we need to actually use, I think, like some Raylib GL function, which says rotate. So angle, that's exactly what we calculated, and we're gonna rotate on z-axis, pretty much do a 2D rotation. So because z is an axis that is pointing into your screen, we're gonna rotate on this z-axis. Let's see whether it does anything. All right, so right now, like the whole thingy rotates. You can pretty much say that it rotates based on some 0, 0. Right, so we actually want every single tile to rotate based on its center. So we need to do some calculations here. First of all, we need to save current state of all the matrices that Raylib uses. In the end, we can pop it, and we need to do some translation. We need to translate the origin somewhere to like center of our tile, center X, center Y, and 0. And then we need to revert the translation. So what we want to do is we want to move the origin into the center of current tile, then do the rotation, and then revert the translation of the origin and draw the rectangle. All right, so what is a center? Vector2 center, vector2. So sum.x, sum.y. So what is a center? Center is pretty much draw x, right, plus tile spacing divided by 2 plus tile size divided by 2. That's pretty much it. Y is the same. So you can check that this stands correctly. So this is the center of each tile. If we run this code now, nothing is going on. And why does that happen? It probably happens because of this angle. We can probably say that yeah. So this value was some, I think, like gradient value, and the dt is so small that there's nothing happening. But once we do the degree conversion, every single small dt, delta time, is much bigger in radians, or in degrees, than in radians. So the effect is actually visible. So before we do this calculation, the rotation is happening, but it's so small that you will need to wait for a very long time before you see it. All right, so one thing I notice is that our visited tiles are also rotating, and we do not want that. So really what we want to tell here is that if tile state is empty tile, then we apply this. Otherwise, just give it an angle 0 always. Which means that we're only applying rotation to our empty tiles. You can also see that every single of them is using its own rotation period. So looks kind of nice. Maybe it is a bit slow. To increase its speed, we can multiply it. Let's say by pi. Pi is like 314, and everything is like rotating a bit faster. We don't really need to multiply by pi, it's just a constant. We can multiply by 10, it will be just much faster, right? So this just looks cool, but you can pretty much find some constant that you can use for the speed that you would like to achieve. Now, this is pretty much everything that our grid needs. The only thing that is different from the final result that I showed you in the beginning is that we have twice as many as rows, twice as many columns, the size is less, spacing is less. And now if we run it, this is exactly how our final grid is going to look like. So next time we're gonna try and add our snake, just the snake, no food, no enemies, nothing, and try to control it on the board. I hope you liked it, so please like the video. If you would like to receive an update, you like this kind of projects, don't forget to subscribe to the channel. Thank you, and I'll see you next time.